Okay, so let's go back to Green's theorem. Now, it's a property of the Laplacian. So it is in the forms that we are using it. So basically, we need to solve this equation with certain boundary conditions. Now, it is possible to convert this equation to an integral equation with, basically solve it explicitly using another solution. So now the Green theorem, let's start with the Green theorem. It states that if you have one function phi and the other and another function psi, on one hand this is equal to divergence of psi gradient of phi minus gradient of psi scalar product with gradient of phi. Okay, this is one vector identity we know. Now the idea is just integrate this over a given volume. D cubed R over a given volume. This should be equal to the integral, again, over the same volume of the divergence of psi gradient phi minus gradient of psi gradient of phi. And now what we can do is here we have the divergence of a gradient, so we can just convert it to a surface integral. Or more generally, we can say that over a volume, d cubed r psi Laplacian of phi plus over the same volume, d cubed r gradient of psi gradient of phi. So we have these two volume integrals. Whatever these functions phi and psi are, these volume integrals have to be equal to the surface integral over the boundary of this volume. Or this we can also write as over the boundary of the volume psi del phi by del n ds, where this del phi by del n is nothing but the normal vector scalar product, the gradient of phi. This is how we define the derivative with respect to the normal coordinate. So this is what's called the first Green theorem. Now the second one is, for us it will be more useful. The second one, to obtain the second one, you just exchange phi and psi. So on one hand we have this equation, this should be true for any psi and phi. Well, we can just exchange psi and phi. It should also be true that the integral of phi, Laplacian of psi, plus over the volume, gradient of phi, gradient of psi should be equal to, again over this boundary, phi, derivative of psi with respect to n. This should also be true. But then we can just subtract them side by side. Over the volume, d cubed r psi del squared phi minus phi del squared psi. This should be equal to the integral over the volume psi del phi by del n minus phi del psi by del n. This is what we call the Green theorem. Well, if you want, you can even obtain this theorem also directly by noting that this difference is nothing but the divergence of psi gradient of phi minus phi gradient of psi. So the right hand, if you integrate over a given volume, the right hand side just becomes a surface integral. So this is true for any function, whatever function you can think of, this should be true. So this is the second Green theorem. Now we are specializing to our case. Now we want to find the solution of this equation. Plus suitable boundary conditions, we will also look at what boundary conditions we need. So what we do is we assume that we know the solution of this equation. This is a function of r and r prime. We assume that we know one solution of this equation. Now, which solution? Arbitrary. I mean, we don't yet specify it, but we are just assuming that we know one solution. Now, if we know one solution, let psi to be equal to phi. Sorry, let psi to be psi of, let's say these are over r prime, psi of r prime to be g of r prime. And of course, these are Laplacian with respect to r prime. Now, if we just put it back over the volume, d cubed r prime, g Laplacian of phi. Well, Laplacian of phi, we know that that is equal to minus 4 pi rho. Minus phi, Laplacian of psi is nothing but minus 4 pi to the Dirac delta. This is the left-hand side. Well, the right-hand side, there is nothing much we can do about that. Volume psi is our g del phi by del n minus phi del g by del n. Now we can do some of the integrals. We can just take that the Dirac delta integral using the properties of the Dirac delta. So we have phi at the point r times 4 pi is equal to 4 pi d cubed r prime g of r prime rho of r prime plus integral over the boundary of g d phi by dn minus phi del g by del n. Or if we divide by 4 pi everywhere, phi of r is equal to d cubed r prime g of r prime rho of r prime plus 1 over 4 pi g del phi over del n minus phi del g over del n. So this is the solution phi. Remember, to solve for phi, we need that satisfies the given boundary condition. We have to know the value or the derivative of the value of the phi or its derivative at the boundary. But still we have one problem. If you look at this, that boundary integral, it contains both phi and phi, the derivative of phi. So what we can do is, we said that, okay, g satisfies this equation, but to solve a differential equation, we need a boundary condition. We didn't yet specify the boundary condition. So now we can choose our boundary condition. If phi on the boundary if we know the phi on the boundary, we don't know the derivative, So we have to somehow get rid of G over there. Set G equal to 0 on the boundary. This we can do. I mean, we have the differential equation, we have to choose a boundary condition, and the boundary condition that if we choose the zero boundary condition for this G, which is usually called the Green's function, in that case, the first term is 0, so just knowing phi on the boundary is enough to determine what the value of phi is. Now, if instead of the value, if we know the derivative, is known. Well, in fact, if we only know the derivative of phi, we cannot really uniquely determine phi. Basically because, well, the Poisson equation tells me the second derivative. On the boundary, I know the derivative. So if I just shift my phi by a constant, nothing actually changes. So both the boundary condition is satisfied and also the Poisson equation is still satisfied. So if only the derivative of phi is given, we can determine phi only up to a constant. Well, for us it is not physical, so we don't really care about this ambiguity. But in this case, we need to set G. If I am not wrong, it should be equal to 4 pi over V. Del G by del N should be equal to 4 pi over V. Now, if this is the case, then del G over del N is 4 pi over V. We are not really getting rid of the term that contains the phi on the value of phi on the boundary, but that term just becomes the average of phi on the boundary, which is just a constant. So in fact, that term we can basically ignore. And the reason why we cannot set the derivative of G to 0 is, remember, G is, and physically it just corresponds to the electric field, the potential created by a point charge. And the derivative with respect to the normal would correspond to the electric field created by the point charge in the normal direction. And just Gauss theorem basically tells us that the integral of that electric field should be equal to the 1. Or some constant. We cannot just set it to 0. So that's why we cannot set the derivative of G on the boundary to be 0. So we already know what the differential equation that G satisfies. Now we can choose, we are free, I mean, the G is a function that we define. We are defining it. So we are free to choose the boundary condition on G. So either we choose the G equal to 0 or the derivative of G is constant on our boundary. Then we get rid of one or the other term in that surface integral. And basically we know everything. If we determine G, to determine phi, we just need to evaluate that integral of the product of G and the charge density, and then add the term that contains the boundary values of phi, which we already know. So the solution is known. For any boundary condition, by the way. So for example, if you want to have, if you know the value of phi on the boundary, which can be as complicated as you like, it's enough to solve for the point charge with 0 boundary condition. So we first solve for G, which satisfies the 0 boundary condition, take that G, put it in this integral, and then the result will give us the phi with that complicated boundary value. So this basically tells us that we don't need to worry about arbitrary boundary values. It's enough to solve for 0 boundary values. So that's why most of the time we are basically solving 0 boundary condition problems, unit charge with some boundary at 0 potential. But that is kind of enough. Any other boundary value, just put it here. In fact, even if you have, for example, a region of space which doesn't have any charge, to solve with some complicated boundary value, To solve that problem, just solve the point charge with zero boundary boundary condition. Take the result, put it in this integral with rho equal to 0. Again, you're done. The difficult part is how to determine this g. Now, to interpret what this g is, so you see this g satisfies this Laplace equation, this Poisson equation. Well, you can set g is equal to 1 over r minus r prime plus some f r prime. So this Laplacian of g would be equal to minus 4 pi Dirac delta r minus r prime plus the Laplacian of f, and hence f satisfies the Laplace equation. Now 1 over r minus r prime, in this case if you just put it over here, g has this 1 over r minus r prime piece. Rho is the charge density inside our volume. So if we didn't have any other charge anywhere else, the potential will be just the integral of rho divided by r minus r prime. But we have this boundary condition which we somehow impose. But to be able to impose that boundary condition, there has to be some charges somewhere else. Either on the boundary, we can, for example, put a conductor on the boundary, choose the potential on the boundary. Well, then on this conductor, there will be charges contributing to the potential. And this F term basically tells us how these other charges contribute to our potential. And its Laplacian is 0. Now that also makes sense. Its Laplacian is 0 in our volume. It will be corresponding to some other charges outside our volume. So those the charge density corresponding to that other charge will be 0 in our volume. So F satisfies the Laplacian in our volume. So this is the basic idea of the Green's theorem. For example, let's discuss an example. Let's take, we have our sphere. On the sphere, you can say that the top hemisphere is at the potential plus V0, the bottom hemisphere is at the potential minus V0. And you can choose a more complicated potential here. Or, you can say it's a conductor, non-conductor, etc. And then there is a charge density over here, somewhere else. So what is the potential? Everywhere. Now, Green's theorem tells us that instead of this problem, forget this problem. Solve this one first. A grounded conducting sphere, because it's at 0 potential, and we have this point charge over here. Q is equal to plus 1. So if you solve this problem, then the solution of the previous one you can just obtain by using Green's theorem. Our G will be 0 on the boundary. The potential will be 0 on the boundary. Then we need to take the derivative. The boundary is, the n normal direction is the radial direction. We have to take the derivative with respect to r over here. Phi, well, it's V0 at the top hemisphere, minus V0 on the bottom hemisphere. Just put those values. Here we know, we have to solve, we already know G, we know what rho is, and well, we are done. Well, how do we solve this? What we do is we basically, how do you solve this problem? Where is the image? Here. On the left hand side, or on the right side of the left side, right side.
Closer to the charge.
Imagine you have this sphere and you are looking at the sphere. Does your image on the spherical mirror look closer to you or further away? It's closer. The image charge is over here, Q prime, and Q prime is minus Q times R over D. R is the radius, D is this distance. Minus R over D, and then D prime, the distance of this image, is R squared over D. So this is at the point, let's say R prime. This is the vector R prime. Now we need to find the potential at the point R. Well, we can just write it down straight away. This is Q over R minus R prime. This is the potential created by the charge at R prime. This is D. This is D prime. Well, just the definition. I mean, how do we derive these? We can discuss it after this problem. So how do we find the image charge? The potential is Q over R minus R prime plus Q prime over R minus, well, D prime at a D prime distance in the direction of R prime over D. And remember, D is nothing but the magnitude of R prime. So let's just, R minus R prime is R minus R prime squared, square root. This is R squared plus R prime squared minus 2R R prime cosine gamma. Gamma is this angle. And R minus D prime, R prime over D is, well, I will just do the same trick, R minus R prime D prime over D squared, which is square root of R minus R prime. Well, D prime over D is R squared over D squared. This is R squared plus R prime squared, R to the 4 over D to the 4, minus twice R prime, R squared over D squared cosine gamma, raised to the power 1/2. R minus D prime, R prime over D is equal to R squared plus R to the 4 divided by R prime squared minus twice R squared divided by R prime cosine gamma, where D again is equal to R prime. So basically we know the potential. It looks like a complicated expression because this gamma, you see, here you will be taking an integral over R prime. So this gamma will depend on the angles of both R prime and also R. So that you have to take into account. In fact, cosine gamma was, if I am not wrong, this was cosine theta prime minus sine theta sine theta prime cosine phi minus phi prime. Check. It should have such an expression. But basically, you have converted your problem of the differential equation to a problem of integration. In the worst case, tell the computer to do the integral. So you can obtain this phi. You can just integrate them numerically. Now, any questions on how do we apply it? Now let's see how we found that image. This is Q. Well, the image should be somewhere along this line because of the symmetry of the problem. I mean, nothing should change if you rotate, nothing changes in our system if you just rotate our system around that dashed axis. So it should be even true if we replace our system with this point charge plus the image. So it should be along that line. Well, I don't really know where it is. Let's just assume it over here. And let me call this distance d prime, this distance d, the image charge is q prime. Well, if it is on the other side of the center, then d prime will turn out to be negative. And it is a grounded sphere. So if we just pick up any point over here, this r, just for simplicity, let's choose this to be our x-axis. The potential at the point r is just q over r minus d x hat. It's the distance from the plus q charge, plus q prime over r minus d prime x hat. This is the distance from the image charge. And just by taking the square and then the square root, you can just write this in the forms q over r squared plus d squared minus 2rd cosine gamma plus q prime over square root of r squared plus d prime squared minus 2rd prime cosine gamma. And this should be on the boundary when the radius is equal to the radius, when my point is at a distance equal to the radius of my sphere. This should be 0 for all values of gamma. So gamma dependence of the first term should cancel the gamma dependence of the second term. Now, if you want, you can just make a Taylor expansion in terms of cosine gamma and set the coefficients equal to 0. That's the one way you can go ahead. That will give you infinitely many equations which will have a single solution. Or what you can do is just observe this q over r square root of 1 plus d over r squared minus 2 d over r cosine gamma plus q prime over d prime square root of 1, or let me do it the other way around. Let me take the larger of the distances out from both of those square roots. So the larger distance is d. Here the larger distance is r. So the factor that we are adding to 1 is less than 1, typically. So we need to have this cancellation, and the easiest way to have this cancellation is Now this is capital R. We are on the surface of the sphere. So the simplest way to get the cancellation is the two square roots have to be equal. So if we have R over D is equal to D prime over R, then those ratios in the square roots are the same. So the square roots are the same. And Q over D plus Q prime over R. Now, since the square roots are the same, we can take them out in a common factor. What remains as a product is this ratio, and if we set this ratio to equal to 0, then the potential is 0. So the second equation tells me that Q prime is equal to minus Q R over D. And this equation tells me that D prime is equal to R squared over D. So now we have one solution of our potential problem. So you see what the conditions we are having is that we should find a potential which satisfies the Poisson equation with a Dirac delta charge density outside our sphere. And on the sphere it should be 0. So here, if these conditions are satisfied, we have a potential, this one, which satisfies the Poisson's equation with a Dirac delta charge density at the position of our charge outside our volume, and it is 0 on the boundary. Then we have the uniqueness theorem, which states that since the solution is unique, if you have one solution, that is the only one, there is no other one. So kind of it was a trial and error. We tried a solution. We tried a solution which which satisfied our properties. And then it has to be the solution. Not always, in this problem it was enough to have one image charge to satisfy my boundary conditions. Now we can have another question. This time it is not grounded. And then we put some image charge over here, some real charge over there. Now what? It's not grounded, so the potential need not be 0. Again, we can give it a try. Well, the surface has to be an equipotential. And the electric field should be such that within that sphere, the total charge should be 0. Those are our conditions now. We don't know the value of the potential at the surface, but what we know is that the potential should be constant on the surface, that is one condition. Plus, once we determine the potential, you know the electric field, and once you know the electric field, you know the charge in a given volume. Within that volume, the charge should be 0, within the volume of the sphere. Well, again, we can do a similar thing. We have a Q prime over here. If we put a Q prime over there, in that case, the surface of the sphere is an equipotential, 0 potential. It satisfies our Poisson's equation outside the sphere, but nevertheless, it doesn't satisfy the condition that within that volume, the charge should be 0. We can make the charge to be 0 within that volume without spoiling the property that the surface should be an equipotential surface by just putting a charge at the middle. Now we have 2 image charges, not just 1. Now with this configuration, we know that the surface of the sphere is an equipotential surface because the potential of plus Q plus the potential of Q prime makes sure that the potential on the surface of our sphere is 0. And then we have this additional potential created by the charge minus Q prime, but that potential is just a constant on the surface of our sphere. So the surface of the sphere is an equipotential in this configuration. Plus the net charge in the volume of the sphere is 0. So the potential corresponding to these 3 charges satisfies the Poisson's equation in my volume, satisfies my boundary conditions. So it's unique. We are done. So in this case, a single charge creates two images. Now the method of images is basically a trial and error. So you have a given configuration, you just try some point charges inside in a region where the electric field, outside your region. So in this problem we are interested in finding the electric field in our volume which is outside the sphere. So the image charges has to go inside the sphere so that they will not spoil our Poisson's equation in the volume that I am interested in. Now, any questions on these? Method of images, Green's theorem. Let's find the Green's function inside the sphere. So the problem that we are interested in, let's say we have this sphere. Inside the sphere we might have some charge distribution. On the sphere we might have the boundary condition that on the surface phi should be equal to V of the potential phi, V of theta, and phi. So for example, if there is such a problem, the first thing you need to do is find the Green's function inside. Now the Green's function inside it should satisfy this equation. So this is our sphere. We have our point charge somewhere over there. Let's say that is R prime. And it is grounded. Well, there are several means of doing it. One, you can use the separation of variables in spherical coordinates. You can separate your problem into the volume within that dashed sphere and outside, solve your Poisson's Laplace equation in both domains, and then match them at this dashed sphere. That is one way. Another method is use method of images. The idea is basically the same. If you go back over here, you see it is almost exactly like this problem, but the difference is that the charge is not inside, is not outside, but it is inside. The solution is also exactly the same. Q prime is the image of Q, or Q is the image of Q prime. You can go both ways.
If you draw a big circle and big sphere around this sphere and charge Q, then the problem is the same.
No, I don't need to draw another big sphere around it. I mean, this is enough. So, you see, well, let me put that R prime somewhere else. This is my R prime. So there will be an image charge. You see, Green's theorem is the solution of a point charge with unit charge. So here we will have an image, let's call this time Q prime, at a distance D prime, where this time D prime will be R squared over R prime, and Q prime will be 1 minus 1 times R over R prime. Because if we have these two charges, then the potential. Okay, so what is important is you have to put some charges outside your volume. Well, Q prime is outside my volume. You have to choose their position and magnitude such that it should satisfy your boundary condition. In this case, we should have the zero boundary condition. But these charges already satisfy the zero boundary condition. And, well, that's all. So the potential anywhere inside phi at the point R is nothing but 1 over R minus R prime minus R over R prime 1 over R minus D prime R prime hat. So this is the Green's function. Let's put some of the definitions. R prime minus R over R prime 1 over R minus, well, D prime is R squared, the radius squared divided by R prime. And this R prime is R vector, R prime vector over R prime. This is equal to 1 over R minus R prime minus R over, if I just multiply with R prime everywhere, R prime in the R hat R direction minus R squared over R prime hat. Right, yes. So this is our Green's function. It is zero on the surface. It satisfies my Poisson's equation inside my volume. Is it symmetrical with respect to the exchange of R and R prime? Because we said that the Green's function has to be symmetrical. Well, in this form, it doesn't look symmetrical. Let's write it in a different form. Well, the first one is symmetrical, so let's just keep it there. Minus R over R prime squared, R squared, minus R to the 4, plus R to the 4, and minus twice R prime, R squared, R cosine gamma to the power 1/2. The first term is symmetrical, the second term is symmetrical, and the third term is also symmetrical because gamma is the angle between the two. If you just change r and r prime, gamma doesn't change. So it is symmetrical, so as the Green's function should be. That is, we had a proof for the fact that the Green's function in the Dirichlet boundary condition, that is with zero boundary condition, it has to be symmetrical. And this is symmetrical. Let's give a break and then we can continue after the break.